Hi everyone, and welcome to Advent of Code Day 25, Snow Overload, final Advent of Code for 2023. In this video, I'll be going over my solution written in Python and sort of how I approach the problem. Let's get right into it. So in this problem, we're given an input that looks like this, which is the adjacency list for an undirected graph. So we can see we have nodes. Here we have node JQT is connected to RHN, XHK, and NVD. Note that these are it's an undirected graph, so but edges are only represented once. So we have JQT to RHN, and then there's an implied that we can go the other direction too. Basically, what the question asks us is it tells us that we can remove three edges to have to, and this will result if we pick the right three edges in two different components that are unconnected. So yeah, the graph will be split into two disconnected groups. That's probably the better way to put it. And this is equivalent to saying that the min cut of the graph is 3. And so yeah, let's get into how we go about this. So to start off with, um, we're gonna what we're gonna want to save is this list of edges, which is a tuple of strings, a list of tuple of strings, um, and I only store each edge once. So for example, where we have JQT to RHN, I just put this tuple into the list. I don't put the reverse edge into the list as well. Then I create this set of nodes that will be used to create this list of unique nodes. Then, quite simple, just add to these two lists. We're ending up with nodes original and edges original. Then we have this part of the code that implements Karger's algorithm. And so what Karger's algorithm is it's a randomized algorithm to produce the minimum cut on a connected graph. I'm not going to go over exactly how it works, but the general idea is that you have a graph that looks like this, and you pick a random edge. So here, this is showing you selected this for edge, and you contract it. And when you contract it, it means you merge the nodes on the two edges of the graph. Then you get rid of any self edges, so any edges that go from the node back to itself. And then, yeah, you continue that process until you have only two nodes remaining. Then the number of edges between them, so say on this graph, for example, if we contracted there and then contracted there, all we would be left with is these two nodes and three lines in between them. So that would give us a min cut of 3. And essentially, we can keep doing this algorithm because we're not always going to get the min cut. For example, if we contracted there and then contracted there, we would have 6. This would give us a min cut of 6, which is not the true min cut. So you can see how we implement that. Create a copy of the edges and nodes data structures because we will be modifying those. We also randomly shuffle the edges, and that will randomly shuffle the order that we draw the edges out. Then we create these maps to and node count dictionaries. Maps to will be used whenever we merge a node. For example, when we pick this edge, we can think of that as mapping this node onto this node. Initially, all nodes are mapped to themselves. And then node count, when we map this node to this node, the node count of this is increased by the node count of this. So if this is the original graph, all the node counts would be 1. After we merge, this node count would be 2. And that sort of lets us track. Because at that very end, what we're going to want to return is multiplying the sizes of the two groups together. All right, so then, excuse me. We repeat this process of drawing an edge for the length of the nodes minus 2 times. That'll give us 2 nodes remaining. And what we do is draw an edge, check if it's a valid edge by getting what the node on either end maps to. And if these are different, so if we don't have a self edge, then we will use this edge. Otherwise, we'll keep moving until we get an edge without that's not a self edge. Then we contract the nodes, which means removing the nodes from the nodes list, updating maps to using these 2 lines. This line helps us track that if we map to a node that's mapping to another node, we're not mapping to any nodes that are no longer valid. Then we update the node count. Finally, once this process is done, we count up all of the edges that are not self edges, and if the cut is of size 3, because we know that that's the true min cut, then we'll return the node count of the final 2 nodes. And so yeah, that is actually it for the problem. This will take, it's a randomized algorithm. I found in practice that it does take a little bit of, it can take a little while to run. It seems like it's not finding the min cut of 3 super often. But yeah, that's it for part 1. And this problem actually doesn't have any part 2. So that's it for day 1. And day 25, I mean, and actually it for Advent of Code. Definitely thank you to anyone who's watched and enjoyed my content. I will continue to make some content. What exactly that's going to be is still, I still am figuring out. Put out a video in a few days, um, talking about what my goals are for the future of this channel. But anyways, that was day 25. Thanks for watching. Questions or comments, leave them in the comment section below. And yeah, I'll see you, well, no, day 26, so I guess I can't say that. But yeah, bye.